This video looks at the collision model for reactions. By the end of this video, you should understand the factors determining whether a collision will produce a reaction, understand why activation energy is necessary to start a reaction, and be able to use the collision model to explain why various factors will affect the rate of a reaction. The collision model tells us that molecules must collide in order to react. Recall that in any system of molecules, the molecules are in constant random motion. Therefore, they will collide with each other from time to time. However, only a small fraction of these collisions will actually produce a reaction. There are two factors that determine whether or not a collision will be effective, in other words, produce a reaction. First, the molecules colliding must collide with the proper orientation, meaning they must be lined up in the right way. And second, the molecules must collide with enough energy. We'll look at each of these two factors individually. First, we'll look at molecular orientation. Consider the reaction between chlorine and NaCl to produce NO gas and chlorine gas. An effective collision between the two reactant molecules will involve the free chlorine atom colliding with the chlorine end of the NaCl molecule. When that happens, the Cl2 is able to separate from the NO. However, should the free chlorine collide with the other end of the NaCl molecule, the nitrogen end, a fruitful collision will not occur because the chlorine has not hit the proper end of the molecule. The other factor determining whether or not a collision will be successful is the energy of that collision. As we know, molecules must collide with enough energy to break reactant bonds. Reactant bonds must be broken before we can form product bonds. Upon collision, bonds within reactant molecules will stretch and they'll bend. And if the collision has enough energy, those bonds will break, which will allow for a reaction to occur. The activation energy, abbreviated EA, is the minimum energy needed to get a reaction started, or the minimum energy needed to break the reactant bonds. This will vary from reaction to reaction. It's often thought of as an energy barrier, meaning it's the energy that must be achieved in order for reactant bonds to break. Now keep in mind, all of this energy refers to the energy of the collisions between molecules. According to the collision model, molecules must collide in order for reactant bonds to break. When those molecules collide with sufficient energy, they form a temporary transition state called the activated complex. The activated complex is a momentary arrangement of atoms at the very top of this activation energy barrier. Let's look at an energy profile for the reaction between carbon monoxide and nitrogen dioxide. Notice here our reactants, CO and NO2, begin with some amount of energy. If they collide with enough energy, they'll form this momentary arrangement of atoms called the activated complex. At this point, the collision has enough energy to break the bonds between the original reactants and result in new products. In this case, the products are lower in energy than the reactants. Therefore, this is an exothermic reaction. The reaction has released energy to the surroundings. Considering now the energy profile of the reverse reaction between CO2 and NO, here we begin with our CO2 and NO at a relatively low energy. Again, if they're able to collide with enough energy to overcome the activation energy barrier, we get this activated complex or momentary arrangement of atoms before bonds break and products form. This reaction is an endothermic reaction because the products are higher in energy than the reactants, meaning energy has been absorbed from the surroundings. Yet another way of looking at an energy profile is shown here. Notice that collisions that occur at an energy lower than the activation energy barrier may cause molecule bonds to bend and twist, but is not enough to cause them to break or to form the activated complex. Only collisions with enough energy to actually cause reactant bonds to break will result in a reaction. Let's consider some factors that will affect reaction rate. As we go through these factors, we'll consider how each one of them affects reaction rate in terms of the collision model. Since the collision model tells us that molecules must collide to react, anything that changes the frequency of effective collisions will change the reaction rate. Some of these factors include reactant temperature, reactant concentration, physical states of the reactants, and the presence of a catalyst. Let's look at each of these individually. We'll start with temperature. First, it's important to consider the fact that the enthalpy of a reaction, or the change in energy of a reaction, does not affect the reaction rate. In other words, the amount of energy gained or lost by the reaction is not related to its rate. The size of the activation energy, however, will affect the reaction rate. A lower activation energy will result in a faster reaction. This should make sense. If the activation energy is lower, that means more collisions will have enough energy to achieve the activation energy. Likewise, when we consider temperature as a factor affecting reaction rate, as the temperature increases, our collisions will have more energy. Therefore, more of the collisions that occur will have enough energy to overcome the activation energy barrier. Consider this Maxwell-Boltzmann distribution. The dotted line here represents the activation energy, or the minimum energy needed for a reaction to occur. At a low temperature, most of the collisions will occur in this energy range here, meaning they will not have enough energy to produce a reaction. But some will have enough energy. If we raise the temperature, more of our collisions will have more energy, resulting in more collisions with enough energy to overcome the activation energy barrier. Now let's consider concentration. If we have more reactant molecules in a given volume, we'll obviously have more collisions. If we have more collisions, chances are more of those collisions will be effective. Therefore, this will increase the rate of our reaction. You can draw an analogy to playing the lottery. If you play the lottery once, you don't have a very good chance of winning. But if you play the lottery, say, 50 times, you have a much better chance of winning. Therefore, if we have more collisions, we have a better chance of having an effective collision. Notice I've also listed pressure here. If we're dealing with gases at a fixed volume, an increase in concentration is the same as an increase in pressure, since increasing the number of molecules in a given volume will increase the pressure of the gas. Physical states of reactants also matter. Homogeneous reactions, meaning reactions between all gases or all liquids, react relatively quickly. In these phases, the molecules are able to move about, therefore they're able to collide with one another more frequently. Heterogeneous reactions, however, such as gases with solids and liquids with solids, tend to proceed more slowly. Solids have a limited surface area, and since only the molecules at the surface are able to collide with other reactant molecules, this will limit how many collisions we have, and therefore how many effective collisions we have, and therefore the rate. A catalyst will also affect the reaction rate. They do this by lowering the activation energy. We'll look at this in more detail in a later video. That brings us to the end of this video. Let's review our goals. First, we looked at the factors determining whether a collision will produce a reaction, these being molecular orientation and activation energy. Then we looked at why activation energy is necessary to start a reaction. And then we used the collision model to explain why factors such as temperature, concentration, and state of reaction will affect the reaction rate.